The system of hyperreal numbers is a way of treating infinite and infinitesimal quantities. The hyperreals, or non-standard reals, *r, are an extension of the real numbers R that contains numbers greater than anything of the form such a number is infinite, and its reciprocal is infinitesimal. The term hyperreal was introduced by Edwin Hewitt in 1948. The hyperreal numbers satisfy the transfer principle, a rigorous version of Leibniz's heuristic law of continuity. The transfer principle states that true first-order statements about R are also valid in *r. For example, the commutative law of addition, x plus y equals y plus x, holds for the hyperreals just as it does for the reals. Since R is a real closed field, so is *r. Since for all integers n, one also has for all hyperintegers h. The transfer principle for ultrapowers is a consequence of Lew's theorem of 1955. Concerns about the soundness of arguments involving infinitesimals date back to ancient Greek mathematics, with Archimedes replacing such proofs with ones using other techniques such as the method of exhaustion. In the 1960s, Abraham Robinson proved that the hyperreals were logically consistent if and only if the reals were. This puts to rest the fear that any proof involving infinitesimals might be unsound, provided that they were manipulated according to the logical rules that Robinson delineated. The application of hyperreal numbers, and in particular the transfer principle to problems of analysis, is called nonstandard analysis. One immediate application is the definition of the basic concepts of analysis such as derivative and integral in a direct fashion, without passing via logical complications of multiple quantifiers. Thus, the derivative of f becomes for an infinitesimal, where St denotes the standard part function, which rounds off each finite hyperreal to the nearest real. Similarly, the integral is defined as the standard part of a suitable infinite sum. The transfer principle. The idea of the hyperreal system is to extend the real numbers R to form a system *r that includes infinitesimal and infinite numbers, but without changing any of the elementary axioms of algebra. Any statement of the form for any number x that is true for the reals is also true for the hyperreals. For example, the axiom that states for any number x, x plus 0 equals x, still applies. The same is true for quantification over several numbers, e.g., for any numbers x and y. xy equals yx. This ability to carry over statements from the reals to the hyperreals is called the transfer principle. However, statements of the form for any set of numbers s may not carry over. The only properties that differ between the reals and the hyperreals are those that rely on quantification over sets, or other higher-level structures such as functions and relations, which are typically constructed out of sets. Each real set, function, and relation has its natural hyperreal extension, satisfying the same first-order properties. The kinds of logical sentences that obey this restriction on quantification are referred to as statements in first-order logic. The transfer principle, however, doesn't mean that R and *r have identical behavior. For instance, in *r there exists an element omega such that, but there is no such number in R. This is possible because the non-existence of omega cannot be expressed as a first-order statement. Use in analysis. Calculus with algebraic functions in formal notations for non-real quantities have historically appeared in calculus in two contexts: as infinitesimals like dx and as the symbol infinity, used, for example, in limits of integration of improper integrals. As an example of the transfer principle, the statement that for any non-zero number x, 2xx, is true for the real numbers, and it is in the form required by the transfer principle, so it is also true for the hyperreal numbers. This shows that it is not possible to use a generic symbol such as infinity for all the infinite quantities in the hyperreal system. Infinite quantities differ in magnitude from other infinite quantities, and infinitesimals from other infinitesimals. Similarly, the casual use of 1/0 equals infinity is invalid, since the transfer principle applies to the statement that division by 0 is undefined. The rigorous counterpart of such a calculation would be that if epsilon is a non-zero infinitesimal, then 1 epsilon is infinite. For any finite hyperreal number x, its standard part, Saint x, is defined as the unique real number that differs from it only infinitesimally. The derivative of a function y is defined not as dy dx but as the standard part of dy dx. For example, to find the derivative f of the function f equals x2, let dx be a non-zero infinitesimal. Then, the use of the standard part in the definition of the derivative is a rigorous alternative to the traditional practice of neglecting the square of an infinitesimal quantity. After the third line of the differentiation above, the typical method from Newton through the 19th century would have been simply to discard the dx2 term. In the hyperreal system, dx2 0, since dx is non-zero, and the transfer principle can be applied to the statement that the square of any non-zero number is non-zero. However, the quantity dx2 is infinitesimally small compared to dx, that is, the hyperreal system contains a hierarchy of infinitesimal quantities. Integration. One way of defining a definite integral in the hyperreal system is as the standard part of an infinite sum on a hyperfinite lattice, defined as a plus dx, a plus 2 dx, a plus n dx, where dx is infinitesimal, n is an infinite hypernatural, and the lower and upper bounds of integration are a and b equals a plus n dx. Properties. The hyperreals *r form an ordered field containing the rails R as a subfield. Unlike the rails, the hyperreals do not form a standard metric space, but by virtue of their order they carry an order topology. The use of the definite article the in the phrase the hyperreal numbers is somewhat misleading in that there is not a unique ordered field that is referred to in most treatments. However, a 2003 paper by Vladimir Konove and Scheller shows that there is a definable, countably saturated elementary extension of the rails, which therefore has a good claim to the title of the hyperreal numbers. Furthermore, the field obtained by the ultra-power construction from the space of all real sequences is unique up to isomorphism if one assumes the continuum hypothesis. The condition of being a hyperreal field is a stronger one than that of being a real closed field strictly containing R. It is also stronger than that of being a superreal field in the sense of Dale's and Wooden development. The hyperreals can be developed either axiomatically or by more constructively oriented methods. The essence of the axiomatic approach is to assert the existence of at least one infinitesimal number, and the validity of the transfer principle. In the following subsection we give a detailed outline of a more constructive approach. This method allows one to construct the hyperreals if given a set theoretic object called an ultrafilter, but the ultrafilter itself cannot be explicitly constructed. From Leibniz to Robinson. When Newton and Leibniz introduced differentials, they used infinitesimals, and these were still regarded as useful by later mathematicians such as Euler and Cauchy. Nonetheless, these concepts were from the beginning seen as suspect, notably by George Berkeley. Berkeley's criticism centered on a perceived shift in hypothesis in the definition of the derivative in terms of infinitesimals, where dx is assumed to be non-zero at the beginning of the calculation, and to vanish at its conclusion. When in the 1800s calculus was put on a firm footing through the development of the definition of limit by Bolzano, Cauchy, Weierstrass, and others, infinitesimals were largely abandoned, though research in non-Archimedean fields continued. However, in the 1960s Abraham Robinson showed how infinitely large and infinitesimal numbers can be rigorously defined and used to develop the field of non-standard analysis. Robinson developed his theory non-constructively, using model theory. However, it is possible to proceed using only algebra and topology, and proving the transfer principle as a consequence of the definitions. In other words, hyperreal numbers per se, aside from their use in non-standard analysis, have no necessary relationship to model theory or first-order logic, although they were discovered by the application of model-theoretic techniques from logic. Hyperreal fields were in fact originally introduced by Hewitt by purely algebraic techniques, using an ultra-power construction. The ultra-power construction: we are going to construct a hyperreal field via sequences of rails. In fact, we can add and multiply sequences component-wise, for example, and analogously for multiplication. This turns the set of such sequences into a commutative ring, which is in fact a real algebra A. We have a natural embedding of R in A by identifying the real number R with the sequence, and this identification preserves the corresponding algebraic operations of the rails. The intuitive motivation is, for example, to represent an infinitesimal number using a sequence that approaches zero. The inverse of such a sequence would represent an infinite number. As we will see below, the difficulties arise because of the need to define rules for comparing such sequences in a manner that, although inevitably somewhat arbitrary, must be self-consistent and well-defined. For example, we may have two sequences that differ in their first n members, but are equal after that. Such sequences should clearly be considered as representing the same hyperreal number. Similarly, most sequences oscillate randomly forever, and we must find some way of taking such a sequence and interpreting it as, say, whereas a certain infinitesimal number. Comparing sequences is thus a delicate matter. We could, for example, try to define a relation between sequences in a component-wise fashion. But here we run into trouble, since some entries of the first sequence may be bigger than the corresponding entries of the second sequence, and some others may be smaller. It follows that the relation defined in this way is only a partial order. To get around this, we have to specify which positions matter. Since there are infinitely many indices, we don't want finite sets of indices to matter. A consistent choice of index sets that matter is given by any free ultrafilter U on the natural numbers. These can be characterized as ultrafilters that do not contain any finite sets. We think of U as singling out those sets of indices that matter. We write if and only if the set of natural numbers, n, and Bn, is in U. This is a total preorder, and it turns into a total order if we agree not to distinguish between two sequences A and B if A B and BA. With this identification, the ordered field *R of hyperreals is constructed. From an algebraic point of view, U allows us to define a corresponding maximal ideal I in the commutative ring A, and then to define *R as I as the quotient of a commutative ring by a maximal ideal. *R is a field. This is also notated A, U, directly in terms of the free ultrafilter U. The two are equivalent. The maximality of I follows from the possibility of, given the sequence A, constructing a sequence B inverting the non-null elements of A and not altering its null entries. If the set on which A vanishes is not in U, the product AB is identified with the number 1, and any ideal containing 1 must be A. In the resulting field, these A and B are inverses. The field A, U, is an ultrapower of R. Since this field contains R, it has cardinality, at least that of the continuum. Since A has cardinality, it is also no larger than, and hence has the same cardinality as R. One question we might ask is whether, if we had chosen a different free ultrafilter V, the quotient field A, U would be isomorphic as an ordered field to A, V. This question turns out to be equivalent to the continuum hypothesis. In ZFC with the continuum hypothesis we can prove this field is unique up to order isomorphism, and in ZFC with the negation of continuum hypothesis we can prove that there are non-order isomorphic pairs of fields that are both countably indexed, ultrapowers of the rails. For more information about this method of construction, see ultraproduct. An intuitive approach to the ultra-power construction. The following is an intuitive way of understanding the hyperreal numbers. The approach taken here is very close to the one in the book by Goldblatt. Recall that the sequences converging to zero are sometimes called infinitely small. These are almost the infinitesimals in a sense. The true infinitesimals include certain classes of sequences that contain a sequence converging to zero. Let us see where these classes come from. Consider first the sequences of real numbers. They form a ring, that is, one can multiply, add and subtract them, but not always divide by a non-zero element. The real numbers are considered as the constant sequences. The sequence is zero if it is identically zero, that is, n equals 0 for all n. In our ring of sequences one can get ab equals 0 with neither a equals 0 nor b equals 0. Thus, if for two sequences one has ab equals 0, at least one of them should be declared 0. Surprisingly enough, there is a consistent way to do it. As a result, the equivalence classes of sequences that differ by some sequence declared 0 will form a field, which is called a hyperreal field. It will contain the infinitesimals in addition to the ordinary real numbers, as well as infinitely large numbers. Also, every hyperreal that is not infinitely large will be infinitely close to an ordinary real. In other words, it will be the sum of an ordinary real and an infinitesimal. This construction is parallel to the construction of the rails from the rationals given by Cantor. He started with the ring of the Cauchy sequences of rationals and declared all the sequences that converge to 0 to be 0. The result is the rails. It is clear that if, then the union of n is n, so one of the sequences that vanish on two complementary sets should be declared 0. If is declared 0, should be declared 0 too, no matter what is. If both n are declared 0, then should also be declared 0. Now the idea is to single out a bunch U of subsets x of n and to declare that if and only if belongs to U. From the above conditions one can see that from two complementary sets one belongs to U. Any set containing a set that belongs to U also belongs to U. An intersection of any two sets belonging to U belongs to U. Finally, we do not want an empty set to belong to U because then everything becomes 0, as every set contains an empty set. Any family of sets that satisfies is called a filter. If also holds, U is called a no-ultra filter. The only explicitly known example of an ultrafilter is the family of sets containing a given element. Such ultrafilters are called trivial, and if we use it in our construction, we come back to the ordinary real numbers. Any ultrafilter containing a finite set is trivial. It is known that any filter can be extended to an ultrafilter, but the proof uses the axiom of choice. The existence of a non-trivial ultrafilter can be added as an extra axiom, as it is weaker than the axiom of choice. Now if we take a non-trivial ultrafilter and do our construction, we get the hyperreal numbers as a result. If is a real function of a real variable then naturally extends to a hyperreal function of a hyperreal variable by composition, where means the equivalence class of the sequence relative to our ultrafilter. Two sequences being in the same class if and only if the zero set of the difference belongs to our ultrafilter. All the arithmetical expressions and formulas make sense for hyperreals and hold true if they're true for the ordinary reals. One can prove that any finite hyperreal will be of the form where is an ordinary real and is an infinitesimal. Now one can see that is continuous means that is infinitely small whenever is, and is differentiable means that is infinitely small whenever is. Remarkably, if one allows to be hyperreal, the derivative will be automatically continuous. Properties of infinitesimal and infinite numbers. The finite elements f of *r form a local ring, and in fact a valuation ring, with the unique maximal ideal S being the infinitesimals. The quotient f, S is isomorphic to the rails. Hence we have a homomorphic mapping, Saint, from F to R whose kernel consists of the infinitesimals and which sends every element x of F to a unique real number whose difference from x is in S. which is to say, is infinitesimal. Put another way, every finite non-standard real number is very close to a unique real number, in the sense that if x is a finite non-standard real, then there exists one and only one real number saint such that x saint is infinitesimal. This number saint is called the standard part of x, conceptually the same as x to the nearest real number. This operation is in order-preserving homomorphism and hence is well behaved both algebraically and order-theoretically. It is order-preserving though not isotonic, i.e., implies but does not imply. We have, if both x and y are finite. If x is finite and not infinitesimal, x is real if and only if the map saint is continuous with respect to the order topology on the finite hyperreals. In fact, it is locally constant. Hyperreal fields. Suppose X is a Tikhonov space, also called 83.5 space, and C is the algebra of continuous real-valued functions on X. Suppose M is a maximal ideal in C. Then the factor algebra A equals C. M is a totally ordered field F containing the rails. If F strictly contains R, then M is called a hyperreal ideal, and F a hyperreal field. Note that no assumption is being made that the cardinality of F is greater than R. It can in fact have the same cardinality. An important special case is where the topology on X is the discrete topology. In this case, X can be identified with the cardinal number kappa and C with the real algebra of functions from kappa to R. The hyperreal fields we obtain in this case are called ultrapowers of R and are identical to the ultrapowers constructed via free ultrafilters in model theory.